Hi everybody, this is Tom Trams with the next video in the Amiga as a Workstation series. This is also part of the Retro Computing Archaeology series, and since it is December, this is also my DOScember video. You can recall in the previous episodes, we basically put together a heat map application which shows data captured from a number of different temperature sensors across a printed circuit board and visualized them. We did this using writing it in C, using standard operating system techniques, using intuition, using graphics library calls, etc. With this video here, this is a very long-form video, we're actually going to be repeating the whole process for the IBM PC to show essentially what we've had to do on the IBM PC to create the same application. We're going to be doing it entirely in MS-DOS. We're going to be using the IBM C Compiler version 1.0, and because this version of the C Compiler, which is based on Microsoft C version 3.0, does not have any graphics libraries of its own, we also have to roll our own here. And this is part of the process to basically describe the differences between the environments and what we have to do essentially to accommodate them. But not only that, this also serves as essentially a whole bring up here for PC fans to show exactly how I'm going to take and bring up this entire development environment from scratch when we have a brand new PC AT that's been shipped to us. So with that, let's go ahead and let's begin. We'll go ahead, we don't need you anymore, because we're going to be starting entirely from scratch. I'll be using the excellent 86-box emulator, which if you haven't seen it, I'll take and put a link to it in the description. It is a fantastic little emulator package which can emulate any classic PC configuration you could possibly dream of. To use it, we're going to take and make a directory for it because it's going to take and store our hard disk images and various temporary files, non-volatile RAM files, etc. in this folder here. So we'll take and create it here, and then we'll use 86box here by default and just start it. In a few moments it starts up, and you're going to notice right here that our default setting is essentially a standard IBM PC 5150 with 64K of RAM, I think, by default. And cassette basic, nothing there. So yeah, we need to make some changes. Since we're comparing against an Amiga here, we're going to be using a contemporary machine. We're going to be using the IBM AT, which has an 8286 processor in it. We're going to add a floating point unit because we're doing engineering and scientific works applications here. We're not going to use it directly here, but it's here in this machine nonetheless. We'll set the frequency to 8 megahertz since this is a late model AT that's had the new BIOS and all the bits and pieces added to it. So a couple things that we know that we need to do here is that we also need to take and increase the RAM. Yes, PC ATs came with a base memory configuration of 256 kilobytes of memory, just like the Amiga. Ooh, gotta love it, huh? So you will take and put roughly 1 megabyte of RAM in here, no problem. And because the diagnostic software that we need to use to set the system up is going to be thrown for a loop if we don't do this, we need to disable time synchronization. Cool. Okay. So now, in addition, it's set the default display to IBM CGA. We're actually going to take and upgrade that to an EGA. Standard IBM EGA. If we configure it, we'll see it has the maximum amount of memory on it here, which will give us access to all the modes, and we are attached to an EGA monitor, an actual IBM 5154 in this case, in enhanced mode. Okay, nothing special here. We don't have any input devices, no mouse, no joystick. There's no sound card or anything like that, no network card, but we do have a couple of serial ports and a parallel port configured. Nothing really here on our printer port at the moment. we do need to take care of our storage. Our floppy disk controller is handled by an internal controller. There's no real reason to change it. But we do need to set the hard disk controller correctly. In this case, we need to use a WD-1003 AT MFM RLL controller. IBM would OEM this controller to go into the PC-AT itself. And we need to add a hard drive. Now for our hard drive here, we're actually going to be using a fairly standard hard drive geometry here. That's type 3. So we're going to say this is, we're going to call it PC-AT hard drive image. It's an image file. We want it to be just an image file. Nothing special, nice and raw. It's small anyway. And we need to set the drive type appropriately. Now, they sort of sorted this out a little bit strange in terms of hard drive types here. But in our case, what we're looking for is a middle of the road 20 megabyte drive that is 615 cylinders, 4 heads, 17 sectors. This is like an ST225, for example. So this corresponds to hard drive type 2. It needs to go into MFM RLL, and because we set that, we can't set an artificial speed here, so this is going to run as fast as it's going to run. Whatever, it's not going to impact us that much. We set it up, okay, fine. It says remember to partition and format the newly created drive. We're going to do that. We need to take a little change here for the floppy drives. We're going to take and change you to a 1.2 megabyte high density dual mode, meaning it runs at either 300 or 360 RPM, depending on the disk that's in it. And no second floppy drive, because PC-ATs typically didn't come with one from the factory, although you could specify one to be added. So, fine. Okay, looks good to me. No removable devices, no other peripherals. With that, I think we're good to go. We'll go ahead, say don't save this again. We'll save our settings. And it will reboot the machine into our PC, emulated PC-AT. While this is happening, I want to make one little adjustment here. I want to turn this into a resizable window so we can move it. Fine. I'll force 4:3 display ratio, and since this is EGA, etc., I want to add some overscan so we can see the borders and stuff. You'll see that the system options are not set. The battery is dead, hasn't been set, whatever. CMOS is completely empty, and it says run setup. Now, most people at this point would use a third-party setup utility, and many of these IBM PC-AT setup videos that I see that set these things up, they'll use third-party tools because the setup routines are not in the ROM BIOS. They're external, so you have to run something else to use them. The correct tool for the IBM PC-AT is the IBM Advanced Diagnostics disk. Well, where do you get that? Good thing you can actually get that at this wonderful site right here, winworldpc.com. Now, I want to give a moment to thank the guys that run this site here because they have done a very thankless job of collating and bringing together not only a large collection of operating system software, but a support forum so you can understand how to set these things up. In our case, we need diagnostics, the IBM PC Diagnostics disk. And there were many different versions. For PC, then for PC XT, the Advanced, which was for the XT. And finally, there was a version for the convertible, but there was also a version for the IBM PC-AT, version 2. And since this is a late model machine, we can use the Advanced version 2.07 to do that, to get all of our options set. Take that, grab that, there's a disk image inside that, and you can mount that directly using 86box. We'll go into I already have a copy of it here. We'll take and go to 5170 PCAT disks, and advanced diagnostics here, bam. ATG207, da da da. So all we do, we put this disk in the drive, it's in the drive, we press F1 and it will boot into it. At this point, it gives you a part number for the ROS, which is IBM speak for BIOS, ROM BIOS, and the date for that ROM BIOS. This is November 15th of 85, so that makes this a late model IBM AT. There we go. Have you completed running this program since connecting the battery? No, we have not. This is IBM speak for, okay, let's set all the settings then. At which point it gives us the opportunity to set the date. Well, the date, in my case, 12/8/2024. You can do that. It does fine. We can set the time, 11:42:0. Great. That looks good to me. It's counting up, looking okay. Systems options information is required to answer the following questions. Okay. Which disk drives do we have installed? Well, we have one 1.2 megabyte floppy, so we go ahead and install that. Yes, that's cool. How many fixed disks are installed? We have one. Which type is that fixed disk? Which one did I actually select? I freaking forgot at this point. Let me, excuse me for a second while I take a look. Oh, it's a 20 meg, so type 2. Now, what do you type in here for hard drive types? Well, you can see a lot of different places. Just Google for it, PCAT, common PCAT drive types. Here we go. In our case, it's type 2, 615, 4 heads, 17 sectors per track. 2. Yes, this is correct. Primary display, yes, we're looking at the primary display. Yes, that's correct. And yes, there's a math coprocessor. We just have to indicate it. Yes, we have 640K of base memory. That's correct. Yes, we have 384K of extended memory or expansion memory. Yes. So now you see the final list of all the system options right here. This is all set up like this. Are these options correct? Yes. At which point it writes them out and cold starts the machine. One beep, all good. But we have to run this diagnostics disk again. But now that the CMOS setup is correct, we're all good. We're given a menu of options. We are going to be going into system checkout, which basically performs things like low-level formatting and diagnostics and stuff, but there are a number of other utility functions that they provide here. Formatting a disk, copying a disk, preparing a system for moving, which is IBM speak for parking the goddamn hard drive, back when you needed to do such a thing. Setup, which runs through the whole process of what we just did, and finally ending diagnostics. We need to do a system checkout, so 0. It will take and load the system checkout portion of the software, which takes a moment. A big piece of software. And we'll see a complete list of installed devices. Now I want you to look at something here. You can see that these numbers are not consecutive right here. 1 system board, 2, then memory, 17 for fixed disk drives. Yeah, funny enough, if you look at all of these numbers are the prefixes for the various postcodes that the IBM ROS can emit. So 17 for fixed disk drive. So a 1701 postcode error, for example, is a fixed disk controller initialization error. So is the list correct? Yes. Okay. We just want to run the test one time. We don't care. And it gives us, because we asked to do it one time, it gives us the opportunity to say, well, what specific test do you want to run? We want to run test for number 17, fixed disk controller. At which point it says, okay, here's our fixed disk diagnostic menu. We don't need to run any hardware diagnostics on the disk drive itself, but we do need to use the format menu. So we need to go ahead and do 7. And then we need to basically say, okay, we need to do an unconditional format, but read the message down here below. For other options, type the option number followed by comma and the drive. In this case, the first drive is drive C. So we want to do we really want to do, there's a conditional format and there's an unconditional format. In our case, we want to do an unconditional format because we want to format everything on the drive. Unconditional is IBM speak for format everything. This is what's called a low-level format, and normally on PCs of this era, you would be using an external utility, or on PCXTs, you'd be using embedded BIOS code inside the BIOS extension to do this sort of thing, but it's a low-level format. Okay, all data on the fixed disk will be destroyed. Do you want to continue? Yes. Do you want to continue? Are you absolutely sure? It asks you twice. And then it gives you the opportunity to basically take and read out the defects that are on the printed label. Any defects to enter? No. Now, here's the thing. Because we're running an emulation, this failed. That's okay. It's fine. I just wanted to take and show you the process of going through this. With this working as normal, it would take and complete. You'd be sitting here at a cursor for a while, then it would complete, and you would wind up going back to the main menu. You'll notice that the hard drive right here is currently sitting here in a floating state, in an error state right here. This will change when the diagnostic software reinitializes the controller when we exit. Return to fixed disk menu. Okay, fine. Return to control program. And it resets the drive. Okay, you'll notice that there's a controller error here, 1701. That's okay, fine. But at this point, we're basically done. We've low-level formatted the drive, and now we can proceed to the next part of this, which is grabbing a copy of PC-DOS, again from WinWorld PC, and installing it. So PC-DOS 310, disk 01, we'll take and do a Control-Alt-Delete. So now we're booting MS-DOS. This will come up pretty quickly. Enter new date, time, looks good to me. Since we have a real-time clock, all that gets set correctly. Now, if we run FDISK at this point, because we have a fixed disk set up and we've done the low-level format, the controller recognizes it and it lets us go into FDISK. At which point we can basically say, if we look at 4, there's no partitions on the drive, 614 cylinders worth of data, fine. We'll create the DOS partition and we'll say, do you want to use the entire fixed disk for DOS? Yes. It does that, makes it active, and then we reboot. Okay, now with the reboot, we see there's our drive, but there's no file system on it, so it would absolutely go crazy. So we need to put a file system on it. We use the format command like we do for floppy disks. Format drive C. We want to take and add an option for adding system files and for setting a volume label. Yes, all data will be lost. Oh my gosh. And since we're in emulation, this will happen very quickly. Okay, format complete, system transferred. Normally this takes about 5 minutes. So, okay, volume label, we'll call it dev, and we've got 20 megs, 21.4 megabytes of space on this disk. And if you look, there it is, there's command com, and at this point, it will literally take, you can literally take and boot into it. But we want to take and make things a bit more hospitable. So the first thing we need to do, we need to take and copy the utilities from the first 2 disks, DOS disks, onto the hard drive so we can use them. We'll make a special directory called DOS so we can use them using mkdir. Go into DOS. And then, yep, we have our disk 01. So we'll take and copy from drive A into DOS. And yes, this actually does mean that command com gets copied here too. That's fine. It's an additional copy of the program. It's not that big. And if for some reason you destroy the one that's on the root, you can copy this one back over. Anyway. You'll notice that we have here on this disk there's a pair of system files, ANSI.SYS, which gives us an enhanced ANSI-capable console. We're not going to use it. And VDisk, which we're going to be using to provide ourselves a RAM drive. But first, let's go ahead and copy the second disk. And since this is the last version of PC-DOS before Microsoft homogenized everything, it still has all of the demo basic programs that IBM had shipped with the PC since time immemorial. You get all sorts of things like exe.bin, you get the linker in here, but you also get a nice little special thing here. Notice down here at the bottom, there is source code for the VDisk sys driver right there. Kind of nice. You can see how the RAM disk driver was made. You also get the debugger. So there we go. All the files copied over. And at this point, we can take and eject. And we'll do a little bit of tidying up to make this environment a bit more hospitable. First thing we need to do is I need to set up a path real quick so that we can reference executables and other directories without having to explicitly specify them. And for this, we'll use path c:\./c:\.DOS. Any executable in the DOS directory now I can run directly. And we're going to use that to run the editor. This is MS-DOS before version 5. So that means the only text editor that you get that's bundled with the system is a line editor called EDLIN. Ironically, EDLIN would survive in MS-DOS as a part of the supplemental disk from version 5.0 onward. So, EDLIN has one parameter, the file that we want to edit. So in this case, we need to take and create a file called CONFIG.SYS, which will add our bits and pieces of what we want to add here. So let's see here. I want to take and add I to insert, give us command. Now we're actually editing the file. We're inserting stuff into the file. And we're going to take and add c-dos vdisk sys. And it takes a couple of parameters. One is the size of the disk itself. We'll say 256K, fine. The second is the sector size. And the third is the maximum number of directory entries that we want to allow in the root directory of vdisk. Okay. Finally, we need to take and specify the number of file handles that we want to use maximum. Files and buffers 20 is plenty. At which point we can hit Control-Z. We can use the L command to show the lines of the file, and it will show up to 24 lines at a time. And you can list the file. Okay, everything looks good. Finally, we can do E to end the edit and save the file. We now have a config.sys file, but we also need to make one on AUTOEXEC. Same thing, new file, I to insert. And I'm going to do this a bit differently here. So we want a prompt, and we want a path. Okay. We've got a couple of lines in here, but I remembered, oh crap, actually I need to take and add something onto the end of that. Maybe I need to add an additional directory. Well, I can take and specify a line to edit by entering its line number, at which point it brings it up. And I can use the standard MS-DOS shortcut keys like F3 to take and enter the data from the last line to come over, and then maybe we add something else. But in our case, I need to take and insert a line above line 1. So I will take and say line 1. Starting here, we'll take and insert a line before. We'll add our echo off. Done, hit enter, goes to line 2, Control Z to end the edit. We do an L to list, and you'll see that echo off is now line 1. Okay, edit, done. CONFIG.SYS, AUTOEXEC.BAT, if we take and reset at this point, Control-Alt-Delete, it'll boot into our new environment, and things are a tad bit more hospitable. So now we've got our VDisk, 256K, sure. 512 sector size, directory entry 64, and so we've got drive C now, 20 meg, drive D, our VDisk. Okay. Now comes the time that we've all been waiting for to install the compiler. Again, the compiler that we're going to be using is IBM C. The IBM C Compiler. This is a rebranded version of Microsoft C version 3.0 with IBM branding all over it. But it is exactly the same compiler. Comes in a box with a manual and 4 360K 5¼ inch disks. You can download it, you can grab it, you can use it. Bam. So with that, you'll notice it's like, a megabyte total. Kind of funny. So we'll go ahead and insert the first disk. Existing image, okay. This is sitting off in another on another system here of my PCXT here, so I'll go into disks, C Compiler, disk 1. The install procedure is entirely manual. And the manual for IBM C, or Microsoft C version 3, shows you how to do this. This manual is not here, so I cannot show you this manual. The closest one I can find is a copy of Microsoft C version 4. But I'll go ahead, since I know how to do this, I will show you exactly how to do the install. The first disk contains the compiler, as well as a demonstration program that you can compile with it for sanity checking. For this, we actually need to make a directory for our compiler stuff to go into, and we'll just call it bin. And we'll copy everything from drive A over to it. This is CC, the front end. That's what you typically run to invoke the compiler. You do not invoke P0, 1, 2, or 3 by yourself. Those are the intermediate passes, with P0 being the preprocessor. So, demo C, you get a demonstration program here. Okay, great. So now we have that. Well, now we need to take and insert the second disk. Existing image, disk 2. And you'll see that this has 3 directories on it. The first directory is called small, and it refers to the C libraries for the small memory model. This is the memory model that we're going to be using, even though we're going to be taking and copying all the memory models to the hard drive here. I won't go into detail as to what 8086 memory models actually are. There were basically a handful of them, small, medium, large, and there were some special ones like compact and huge. And it basically refers to how how you segment up the memory that your program goes into. How much space are you going to allow for code? How much space are you going to allow for data for the code to use? How much space can you allocate for stack, and so on. Since our program is fairly simple and it doesn't need more than 64K for either code or data, we're going to be using small. But we need a place to put this. So we basically come back over here and we make a directory called lib. And lib is going to contain all of the libraries for the small, medium, and large. And you'll see right here, this is libc, the C runtime. libf are the floating point libraries for both real and emulated processors. And you see a couple of bits and pieces of what are called, this is startup code. You need this, the linker will automatically take and put this in. You don't have to specify it. But this is the bootstrap code that any C program needs in order to put itself into a runtime environment where the C code is happy. Parsing arguments, that sort of thing. So, there's that. The second is the linker. Now, if you recall, we have link, and MS-DOS version 3.1 comes with version 2.3 of the linker. But we have another version right here. Turns out the IBM C Compiler comes with version 3 of the linker. So they made this one pretty quickly after the fact. Not a problem. It also contains a handful of libraries that we need to copy into lib, but we need to take and copy the executables into bin. We need to copy the libraries into lib. And we need to copy the object also into lib as well. Finally, I think that's okay. So small linker, and now we have include. Include has its own unique little wrinkle here. You'll notice that we have a number of very basic header files for things like stdio. If you're familiar with C programming, this is immediately evident. There's a special one here called DOS.H, which includes functions for things like calling BIOS services, DOS services, and stuff. And we'll be using that for the graphics library. You have console I/O, bits and pieces, all of that. There's also another niggle up here, and this is that there's a sys directory, and this contains header files for things. If you were to take and port something over from Xenix back to MS-DOS, you would potentially be using these. So there are stub files in here, but you have to copy them over anyway. So we'll copy them. For that, we need to make another directory. And we need to go ahead and make include sys while we're at it. And we need to take and copy into include. And we need to take and copy what's in sys into include sys. Make sure that's all nice and neat. And that concludes the second disk. Finally, okay, that's the second disk. Third disk contains utilities that we need. It contains, among other things, it contains programs to take and pack executables to make them smaller or to modify their various attributes. It contains the librarian, which is used to make shared libraries, which we'll be using to build GRLIB. It contains make, which is used to take and automate build processes, of course, just like Unix make. It's an okay version of make of sorts, but it works much the same. There's mapsim and simdeb, which are used for debugging as well as investigating the symbol tables of your programs and your libraries. Yay. All that needs to be copied. So we'll take and copy that over into bin. And that is everything that is on the third disk. Finally, disk 4 contains the medium and large programming models. All these can just be dumped into lib. Fairly straightforward. But yeah, this is quite literally the install process. Finally, we want to do some more quality of life changes here. We'll go ahead and remove this disk because we're done with it. And we need to take and modify our AUTOEXEC to add some environment variables. Environment variables work just like they do under Linux or Unix. You just have a key and a value. So we need to add a couple of these because the linker is going to use them to point to various paths to make our lives easier. And for the sake of convenience, we're going to put it in the AUTOEXEC at the bottom. We're going to set lib to point to the library folder. We're going to set include point to where our .h files are. And we're going to set temp to point to our RAM disk that we just set up, our V disk, to make compiles that much faster. There you go, man. With all this set up, we also need to take and make one little adjustment on line 3, F3, bring that in, and we will add bin to the back end of this so that we have our compiler tools in our search path. Edit, done. And you'll notice because that we edited an existing file, it created a backup file for us. We don't need it, so we can get rid of it. Back. So, there we go. Set up. We're reasonably in a good space here. So if I take and do a Control-Delete reboot, we should come back into our environment. Everything's set up, everything's nice and neat. And if I take and run CC, there's our C compiler ready to go. Let's do a sanity check and make sure that our C compiler is working as it should. We'll make a directory called hello. And then it will make a hello world application. We want to make sure that our include paths are working correctly and that we're linking to the correct library. So hello world is a good way to test that, especially because we can include stdio.h. Even though we don't have to, because this is KNRC. So EDLIN hello C, new file. We enter in our code just like we do in a full screen editor, except we're just doing it in one line at a time. stdio.h. Because we set our include paths directly, this will work just fine. This is KNRC, so we're not specifying much of anything here. Run out, hello world. Close that bracket, Control Z. If we do a list, we'll see there's our source code right there, ready to go. Edit, it's done. And Robert's your father's brother. Yeah. All we have to do to compile it is run the compiler. You can specify the individual parameters that it needs on the command line, or you can specify them interactively like I'm going to here. I don't have to specify the extender. It will guess it automatically. Okay, fine. And our target object file. We also might want to take and produce a list file. And we have the ability to do an object listing, which basically shows the assembler instructions that are emitted in response. Then it takes and compiles. There it is. We've now set up, our compile is working correctly, and we now have a list file, we have an object file, and we have a code generation file. What got generated? Well, hello list. It's a printer friendly list with a form feed character at the top of each page, so it fits nicely on a standard printed page. Gives you the listing here, gives you the symbols, etc., etc., etc. But you also get code generation. So you get to see what it did, what it sent to its internal assembler, and what wound up getting created in the first place. And as you can see, this is ancient KNRC pre-optimization, so there's a lot of stack juggling. But there you go. Calling out to our standard print, there you go. But we're not done yet. We just have a relocatable object file that we've generated from our compiled code. Now we have to link it. To use that, we need to use the C linker. Okay, fine. All we have to do is specify, okay, hello. Fine, what's our run file? Hello, execute. Do you want a final list file, which is basically just a memory map? Sure. And no other libraries that we need to specify, because we've specified where libs actually are, and because we don't need anything outside of the standard libraries here, we don't have to specify anything here. We hit enter, and a few moments later, we have our hello execute. 5,902 bytes. We run it. There's hello world. Our compiler is working. What got generated on top of all of this? So we've got hello map, and this just gives you a memory map of where all the symbols are in the program that was just linked together. There you go. Since this is a small memory map, everything is in the same segment. So pretty much you have codes in one segment, data in the other, basically. So, okay, hello world works. We are good. So that brings us to the point now. How do we take and write what we need? Because we need to write a graphical program, but we don't have any graphics routines. Thankfully, the IBM EGA adapter the IBM Enhanced Graphics Adapter Manual provides a comprehensive understanding of how the EGA adapter works, both in terms of talking to its BIOS, so that you can, for example, set graphics modes, or to talk to the hardware directly. And in our case, what we're actually going to be doing is using the BIOS interrupt trapped 10H, or int16. And it provides a whole series of graphical functions, just basic things, very basic graphic functions that any real mode software can actually use, something running under MS-DOS or something just running basic 8086. And you got a whole bunch of different things like set your video modes, get your cursor positions, scrolling your windows, setting your background colors, reading and writing characters, but also reading and writing graphics pixels, which we'll be using, and so on and so on. It's not much, but it's enough for us to write this program, and we can easily take and write bindings to take and deal with it. And that's what we're going to be tackling now. So we'll start by basically implementing a C function which takes and uses the call 00 to set the video mode. And that's going to be easy. You'll see that for each of these calls, you have function calls which correspond to the individual 8086 registers that you have to set. We have to set AH to 0, we have to set AL to the desired video mode, and so on and so on. And you'll return if you really want it, you will get something back which basically indicates the current state of certain CRTC registers. Great. We don't need it, but it's there nonetheless. We'll just ignore it. But this is easy enough to implement. All we really have to do, first of all, let's go ahead and make a directory for our graphics library. And then we take and go into it. Okay. And we'll use the same sort of convention to name all of our functions, gr underscore, and then the function that it's going to do. So our first one's going to be gr mode. We'll use EDLIN grmode.c, and we implement our graphics mode here. So a little bit of self-documenting code. The brief parameter m, the graphics mode to set. And then bam, okay, fine. We don't get it. We don't care about the return or anything. Now we're actually going to be using a particular include called DOS.H. And DOS.H includes a number of helper functions for calling either the DOS-specific trap, which is int21, or for calling other interrupt traps, such as interrupt 10 hex, which is what we're using for video. So we're going to take and use this function is called int86 and is defined in DOS.H and implemented in the runtime libraries of each of these programs. But thankfully it's here, so we don't have to implement that, because otherwise we would literally have to take and do a little bit of assembler to take the parameters out of here and mash them together, get do the thing, get the return values, and then pass them back. But anyway, I digress. So we need gr mode. Gr mode has one parameter, that is m, the mode, and it is very careful. I'm going to show you something here. You have to be very careful and be very aware of the size of your data types here. Since we're dealing with, since we're dealing with the byte size sets of the registers, the high and the low, the video mode needs to fit in an 8-bit value, so that's a char. Char m, okay. And now we take, and that's our function implementation right there. And I use the, you may have seen me do it in other videos and whatnot. This is my thing where I immediately take and close any sort of delimiter that I open. It does make using the line editor a bit more interesting, because now I have to take and Control Z to get out, but then I take and go back in, insert back in. So now I'm inserting in between those two curly braces. That's fine. For this, all we really have to do here, this is fairly straightforward. We need a variable to hold our registers that we're going to pass into the int86 function. This is defined in DOS.H. So if you want to see the contents of what's actually here, that's in DOS.H. You can go look at it. Union regs are, right? Finally, we take and, since this is a byte-sized, it goes, this is a union of two sets of structures called H and X. H is for 8-bit values, X is for 16-bit values. That's 0 for setting the mode. So we set AH to 0. We set AL to M. That's it, man. And then all we got to do at that point, int86. And that is the that's the implementation for doing our that's our basic one right there. Except we're going to take and do a little bit of a twist here. We'll go ahead and return the value because we might want it. Sure, why not? But I'm going to do a little bit of a twist here because I want to handle one special mode here. If we come back up here, param m sets the graphics mode to set. I want to add an additional thing on top of that. I want to add okay. Do that. And then I will take and add an additional bit of code right here. If m is less than 0, if it's -1, assume that, then we do this. Else we do this. We'll go ahead and delete that 17 right there. We'll delete 18 here too. Oh, my bad. We need to take and put 17 here. So 19 becomes this. And we'll go ahead and say 20i. We'll add an additional line right here. You'll notice that I'm doing these changes, and as I'm doing these changes, I'm basically just checking the list to see how this particular page of the code looks. So we'll take and do 17. RH00. And if I hit return on the line here, it will go to the next line. Now we've indented it over. So now we have our basic code that we've used before, but we're going to add in 14, we're going to say, we're going to use get video mode instead. Get video mode is 0f, and what you will be returned back is the AL video mode, AH number of character columns, which we don't care about, number, and the active page, whatever. Doesn't really matter. 0f. We'll set AH to 00f, and AL is not going to matter. So this is our finished implementation for GR mode right here. If we get a -1, we return the video mode. Otherwise, we set the video mode to whatever is in int, and we call the result in int86 and return the result of AL, which in our case, if we do -1, will be the current video mode. If we set the video mode, it will be some CRT status register flags. Groovy. That's it. Exit. Okay, let's take and compile it real quick just to see. Oh, R is undefined. We got to fix that. Not a problem. It got lost when I took and did some cleaning up earlier, so we can fix that. Not a problem. For this, all we really need to do is just add a little bit here. We'll add to line 12. There you are. Ready to go. Exit. So there we go. We can go ahead now at this point and do it again. Okay. GR mode is going okay. Now we can go ahead, as part of this whole thing right here, And now we'll actually take, and we've got GR mode. Okay, great, fine. Let's go ahead and implement let's implement a couple of other things here. We'll just go ahead and implement the rest of what we need, and then we'll take and bundle it up into the library, and then we'll use it. Hopefully that'll be well understood here. Let's see. So GR mode, well, the next thing we need is a way to set pixels. That's pretty easy. So EDLIN GR pset, we'll call it pset for pixel set. Brief. With color C. Parameter X, horizontal position. Vertical position. Color. Okay. And again, that's the same thing. We need DOS-H for int86. And we need to make GR set. This is the name of the function, and it has 3 parameters, X, Y, and C. We specify what those parameters are down here. So these are X and Y. If we take a look at what we have here for writing a graphics pixel, the X and Y are using CX and DX. These are the 16-bit wide sections of the registers, so we need to make sure that these are shorts. Okay? You can say unsigned short. And then we won't be using any negative values here, so X and Y. And char C for the color. Boom. Okay, 14i. Union regs R. Function 0C. Color is set in AL. We're always going to be using page 0. Anything we can do to make our lives a bit easier. And now, since we're using a 16-bit register, we use RxCX. And DX for the Y component. That's it. Finally, int 86. We're not grabbing any return values, so we can specify 0 here for the output. Int 86 has 3 values. That is, the first one is the interrupt service that you want to call. The second one is the register structure for the stuff you want to pass into that call. And the third parameter is the same structure for any return values that you want to return back. It will take and copy all of those register values back out again. We don't need it, so 0. Int 86, okay, done. And that's all we need to do here. So we currently have these 2 functions right here ready to go. We have the ability to take and set a graphics mode. We can take and plot a pixel. Okay, great. Looks good to me. We'll take and make sure that it compiles. And that's kind of that was really the promise of using something like C, whatnot, being able to take and write your program in little pieces, build and debug those pieces individually, and then link them together or put them into libraries so that they can be used in much larger programs. You know. So now we've got GR mode, GR pset, each with object files here. And because we modified GR mode, again, we've got a backup file. We'll go ahead and just as a little bit of some house cleaning here, we'll make a CLEAN.BAT file. And that's just going to be that's pretty much Yeah, it's a good start. There might be some more. We'll add some more later. So there's a little bit of, there's a house cleaning function that we can use, just called clean. So there we go. And clean up and get rid of the backup files. Okay, so it got rid of our object files too, but that's fine. So now we've got mode preset. Now we'll add one more for text. Text is pretty simple too. And its whole purpose in life is basically to put a line of text at a particular text position on the screen. Now, because of how the the text routines in the BIOS actually work, these text coordinates are not at pixel positions, but are at text coordinate positions. So if we use, for example, mode 4, which is CGA, 4-color mode, that's 40 columns across, 25 lines down. If we use mode 5, that's CGA 640 by 200, so that's 80 columns by 25 lines, and so on. You have to keep that in mind when you use this. Again, much the same thing. At the desired position, X, Y. This is just a way, I'm showing you basically how we had to take and bootstrap things in the beginning, especially when we were new to a platform. All right, and finally, the null delimited text strings and C-style strings. And you'll see why we do this in a minute and why C-style strings are so prevalent in C. It's because they're very easy to implement. So again, much the same refrain, include DOS.H. Okay, and now grtech, X, Y, and S. I'm not going to provide the provision for setting color here, but if we wanted to, we could add like that, for example. We'll do this. X, Y, and S. Bam, bam. Okay, great. Oops, turns out I need to take and add some variables, char X and Y, and a pointer to the string so that the compiler knows that S is actually a pointer to some chars, any number of chars. Okay. There it is, right there, the beginning of our function prototype, 14i. Now we can actually implement it. Now this actually has to be done in 2 separate sections. Of course, we need our regs like we did before. We need to set our cursor position. And again, that's using function number 2. Set cursor position. So you'll see each of these different functions all have different calling conventions, and you have to be aware of them. We need to take and put the page number in BH. We need to put the row in DH. We need to put the column in DL. Okay, no return values. So, AH, like always before. BH, always page 0. DH is now Y. DL is now X. And again, we go ahead, that puts the text cursor at that position. Okay? This is our text cursor. That's now set, and now we can print the text. And the way we're going to do this is we're going to be iterating through a pointer to some character data. And we'll use a while loop for this. And while S, this is the same as saying while S is not equal to 0. This is the short form of that. So while we don't have a null character, we do the following. We say RHAEH, and I chose to use the teletype output function here. You can see it right here, teletype output. It's the most straightforward text output here without any weird ass surprises. So we have a handful of inputs, AL being the character, BH page number, BL is the color, and those three basically are the inputs for this. Okay, great. All we got to do, RHAH, RHAL. And we want AL to be set to wherever S is currently pointing to. Okay? That will dereference that pointer, put that value directly into AL. RHBL. And we want to go ahead and I'll set the color to white, just as a convenience. Okay? Finally, we do int 86. And we don't care about the return values coming back. Now, once we've done this, it prints the character to the screen. We need to go to the next character. So we increment S, the point where S is currently standing, we increment that. And then we go once more right around the loop again. So if we take a look and see what that actually is here, you'll see it. Print the text, while S, print each character, do the interrupt call, advance the pointer, and continue while S is not 0 or null terminated. And that's why null terminated strings are so prevalent in C. They are extremely easy to implement. Okay. So that's that. Nothing else we need to do there. Let's make sure that this can compile. Looking good so far. Okay. So we've got text, we have that. Okay, great. Looks good. I think I will take and we'll skip past some of the others for right now. We'll just see how things are at this particular point in time. So now we've got a handful of functions that we can use. We have a few. We have 3. And that's enough to get started to know that we have some sanity here. We can, if we wanted to, we could take and put these object files as arguments into C-Link whenever we linked our program. But that would get very unwieldy very quickly, especially as we added, say, a couple of dozen functions. So what makes sense is to take and use the librarian to take and combine these object files into a single file that can be referenced much easier. So gr text, okay, fine. Let's take and build that. Gr mode. grp set. Okay, great. So we've got those three object files ready to go. Now we can use the librarian to take and combine them together into a library. Now we need to give it a library name, and we're going to call this library name GRLIB. Well, that library doesn't exist. You want to create it? Yes. And now the operations. And the simplest operation is basically to say to add the object file to the archive, to the library. So gr mode, gr pset, gr text. There are 3 functions. We can get a list file, so grlib.lst. And now we have a library file which contains our 3 functions. And we have a list so that we can see what functions are in that library and how big they are, where they are inside the library itself. We can take and copy grlib to our library folder. And now we can use it pretty easily. Let's make a quick little test program. Okay. Now, you'll notice I haven't created a header file. This is old school KNR type C. So it will be very lenient as to what it passes through the compiler. If it sees a function that it doesn't know what it is, it will assume that it needs to link that function at some point, and it just needs to handle that during the linking process. And it will try to guess what the parameters are in the whole process to make sure everything works. In our case, it will work out just fine, especially because we're little Indian. Anyway, okay. So we can fudge things a bit until we get a header file that says, okay, these are the functions, this is what they can do. Nah. But we just want to test and make sure that our library is going to function like it's supposed to. And main. Okay, 7i. Okay. Now, I'm going to make a variable called old mode, and old mode is going to get the input of our mode, -1. Remember the -1 that we implemented, say, give me what the current graphics mode is, right? Now, with that, then we can take and turn right around and GR mode into our desired mode that we want to use. We'll use CGA mode as an example here for example graphics mode. Sure, why not? If we take a look at the values that you can use here, you can see all sorts of early IBM graphics modes. And mode 4 is CGA graphics, 4 colors. We set that, okay, GR mode. We deal with these modes in hex because that's what's customary. And then we can turn right around, write some text. Let's say 1010, hello, X and Y of 10, character positions, mind you. Hello, okay? And then we'll take and for I equals 0, I is less than 128, I plus plus, and we'll just quickly use the p set as a test. That is I, and we'll use color 1. Sure. There's our sanity check right there. Finally, we'll go ahead and get care, just to wait for a return or something. And then we will set GR mode back to old mode. We need to make one adjustment here, and I'm going to take an add at line 7 and I. Doesn't matter, you could put it on top, that's fine with me. Okay, so we have just a basic little test program here that we can take and use. Looking good so far. Let's take and build it. CC test, test object. Okay, it built. Now we're going to try and link it. Link test. And I'm going to show you what happens if you don't specify your library that you made. You're going to come up with some unresolved symbols. You're going to come up with exactly the unresolved symbols that that you have for your graphics library. We also have one for get care. Now the reason for that has to do with how get care is implemented in standard I/O. Get C? Get care is a macro that is implemented using get C, and that talks to the file descriptors and stuff directly. So you need standard I/O to get all this stuff defined correctly. But you see an example of a KNR style header file. You'll notice that with these particular function prototypes, the names of the variables are not specified, only their types. So, okay. Yep. We fixed that by basically going say 5i include standard IO.H. Bam. Okay, great. We don't need to include DOS.H, whatever, because all of that code has already been compiled and resolved in the library for GRLIB. So, yeah, that's fine. And I don't care. There we go. That's fine. So, we got that, and we take and build it. We should be okay now. Test, make sure that's okay. Very good. Now, when we run CLink again, we're going to do this again, and I'm going to see. You saw the unresolved symbols. We fixed one of them. Test object, test execute, null maps. But we need to specify our library that we used here to resolve the remaining symbols. Just specify GRLIB. And since it's in the lib directory, we copied it there, it's there. It resolved everything, no error messages, and we wind up with our test program. We run it. We see our test program running right here as expected with the text and the line going across the screen, everything looking good. Our graphics library is starting to take shape. Cool, huh? Hit return, video mode goes back to where it was. So, now what? Now we can continue implementing the remaining functions. Next one that we're going to implement, we need to implement, we're going to go ahead and just implement line. Line is a Bresenham line function here. There's a lot of code here that I'm just going to breeze through. If you really want to understand the ins and outs of Bresenham line drawing functions, there are plenty of tutorials, both in terms of YouTube and printed material to explain how Bresenham actually works. I won't go over it too much. New file as before. Okay. I'm literally just going to do this as straightforward as I possibly can. I'm not going to, I'm just going to type this in line for line here. So, ran. Line 1, beginning, the beginning, x2, ending, x coordinate, ending y coordinate. So we got those two, and we have a parameter for color. So there's a lot of parameters for this particular thing. There we go. This culminates in our line x1, y1, x2, y2, c. Lots of parameters. Good thing we can put most of them on one line. These all are 16-bit values, so again, short, fine, char C, and now we start implementing. We need the dx and the dy for the slopes, as well as step x and step y values. We need to calculate the difference between x2 and x1, put that in dx, y2 and y1, put that in dy, and we need to use that. The sign of those two values will pretty much determine the direction that the line needs to go. We need to take that into account. If dx is less than 0, the sign is backwards, so we have to flip things around a bit. Step x -1, and so on. Else step X is positive, and we don't have to flip the sign. Same thing for dy. Flip the sign, set the step in the opposite direction. Otherwise, boom. We do a little bit, we do a doubling of the dx and dy values. Helps us with the fractional calculations. Then we go ahead and set our initial point. X1, Y1, C, using our GRP set that we defined earlier. If, now this next piece basically determines whether or not we are drawing a shallow or a steep line, whether dx is greater than dy or vice versa. And we alter the algorithm a little bit depending on that. Okay. Yeah, fraction equals dy minus. Remember that we did this doubling earlier so that we could make the fractional value. It makes it easier to deal with the fractional value. Okay. All right. While x1 is not x2, while because we're marching up x1's value towards x2. We take and step y, fraction, and remove the fractional value. Iterate it down. x1, and then we increase x1's value so that it approaches x2. Fraction, dy, and GRP set. X1, Y1, C. Okay, see? So while that's happening, groovy. Well, so there's, so while, did I? Oh shit. I made a mistake. God damn it. I will take and type that again. So here we go. We're going to take and do that a little bit differently. So 49 to 57D. 43L. Here we go. Type that again. So you can see I can give ranges to delete commands and that sort of thing so I can remove lines. Let's type that again. I wasn't paying close enough attention. Fraction. Then, yeah. If fraction is this, then we do x1, fx, fraction, approaching x2. So now, then we get rid of the little bit of the fraction value. Iterate it down, and we end up with y1, step y, fraction, dy, fraction, sorry, step y, fraction, dx, integrate, do the next step of the integration. So, GRP set, x1, and plot the next point. And that gives us and that's the shallow line. Now we're going to do it for the steep lines. Much the same thing, except it's backwards. Kind of sideways. See, you're going against the other component now. So while y1 is not approaching y2. we do this. Finally, plot again. Now, oddly and interestingly enough, we could probably take and refactor this ever so slightly, but this is where it is right now at this particular point in time. So we do that. Okay, fine. We close this part of the brace, and we close this part of the function. Then the function is now complete. There's our line drawing function. Phew. Okay, a little bit of a windy function there. Basic Bresenham. Okay, so we've got GRLIN looking good, and now we can go on, because now that we have lines, we can do things like making functions that draw boxes. This will be a function that calls GRLIN, grpset, etc. Nice and simple. Actually, let's take and skip GRLIN. We don't really need it. I'll just implement grbox, and that'll be the core of our library. grbox. So, param. Again, parameters are much the same for lines, ironically. Ending x coordinate of bar. Ending y coordinate of bar. That's it. GR bar. And oh yeah, desired color. But I'll go ahead and add it right there. Much the same thing. Short x1, y1, x2, y2. RC. Much the same thing here, except we're just using repeated calls to grLIN, decrementing y here to take control our little bar. It's a hack, but it's something to get us started. So in y1, if y1 is greater than y2, that is, if the coordinates are somehow flipped, then we take and we change the direction of how the lines need to go. Otherwise, there you go. Boom. And while that's going on, then we take and we use a do while loop here because we want this to happen at least once. Draw the line, increase the line's slope by its direction, while we march up the line. That's it. That's our implementation of bar right there. Exit, and we'll take and compile it and make sure it's okay. Okay, so now we have all our bits and pieces. Now we can take and build our graphics library. We'll use the librarian like we did before to assemble our library. I'm going to delete the library in question. yeah. There we go. We have all the bits and pieces. Let's see, object, we should have 4 or 5 functions. Okay. Text, mode, pset, line, and bar. Okay. So lib, grlib, yes, create it, operations, gr mode, gr text, gr pset, gr text, gr line, gr bar. There we go. We put our list file. There's our library. Okay, with our functions. Okay, grline, bar, everything we now need. And our graphics library is reasonably complete. We can now actually get some stuff done. One of the things that we might want to be able to do, though, is to be able to build our library cleanly. So for that, we actually need to take and make a make file real quick that Microsoft Make can deal with. We can easily do that. Now, as we do these sorts of things, let's see here. There we go. Oop, I accidentally hit edit in my other window here. I don't want to do that. Let's make GRLIB.MAK. Simple make file. And make files at their most basic consist of essentially artifacts that you need to make and what they depend on and the commands that you need to execute to create those artifacts based on what you depend on. So, start off with, we need to be able to compile grmode.c, okay? cc grmode. Now, for each one of these, you have what you're going to make. And actually, I need to type this all over again, so I might as well just queue and do this all over again. Let's abort the edit. My bad. Insert. grmode. We need to create grmode object. And that needs to be made from grmode C. So anytime grmode C changes, grmode object needs to be rebuilt. And to do that, we need to enter the command cc, like call a cross compiler for grmode. Now, there's a special thing. Normally, you would need to, if you were specifying different parameters on the command line here, you would have to take and specify, for example, the C file, the resulting object file, the list file, and the resulting code file. You would need to specify all of that for the C compiler not to ask you the next question. But there's a special shortcut. You can either put commas for parameters that you don't want to set, or if you don't want to set any more parameters and use the defaults for everything else, you can use a semicolon. So there we go. grmode, grpset, grpset, text object, again, grline, so we're building each individual piece individually, depending on whether we need to or not. And gr bar. Finally, we need to build the library itself. And that is built from grmode object, grpset object, grtext object, grline object, grbar object. Furthermore, the command that we need to do is lib. We need to go ahead, and I'll delete the library here. And then we'll do lib, grlib, grmode, grpset, grtext, grline, grbar. And we do want a listing, so I'll go ahead and provide that listing, grlib.list. This is actually specified in the Microsoft C manual in the make chapter, so it can show you how to call the library and to take and the parameters that you need to pass in. So there we go, bam. And then we take, as a convenience method, we'll go ahead and copy grlib.lib, the lib. Okay, fine. And we'll go ahead and, just for the sake of it here, grlib.h, which we haven't made yet, we'll take and copy that to include. And that's the end of our make file. So there we go. We can now, as the final part of this, we'll make one more file. We'll make a header file called grlib.h. And you could use this header file, for example, to make a number of conveniences. Let's say, for example, I'm going to go ahead and make a common pattern that I do in my C programs. And if we don't define grlib.h, we'll go ahead and define it. One, and then put our header file inside of this, and this is a guard. This works pretty much everywhere that there's a Unix style C preprocessor. So here we go, there we go, bam. At which point I can now take and do 8i, and we'll start building our prototypes. First things first, we want to add some defines. EGA, let's say mode EGA. Mode EGA 640-216, so fine. Let's say 0x0D. Well, that's, sorry, 0x0E. 640 by 200 by 216 is what we're going to use for our graphics mode here. We can use this space to define any convenience macros that we need, any data structures that we need, but more importantly, any function prototypes that we also need. Int, let's say int grmode. Grmode, of course, has a single value that is a char. See? And grpset has a short, and char. We could say that they're void, but it doesn't, since I didn't specify that in the compiler there, it doesn't really matter. So grtext is X, Y, and S, so that's char, and char. Just like that. Let me double make sure that that's 100% correct. Yep, char, and pointer to char. Okay, and gr line, which is short, x1, y1, x2, y2, and char. All of this is so that the compiler can catch any particular slip up in parameters. At least attempt to. BR bar. And again, short, hair. Same goofy thing going on here. So there are our function prototypes. There's our little convenience macro, and I'll add another one here. Let's go ahead and add another one here for mode get -1. Boom. So we've got some defines, we've got some prototypes, and I'll go ahead and add an additional nice little bit of pretty printing right there. There's our header file. Our header file can now be used. Bam. There we go. Now we can go ahead and run our clean function to clean everything up. Back, object, and lib. Okay, that's good. Nice and clean list. Oh yeah, I need to add one for. Let me add one for the list. Okay, so clean. Get all that out. So we have this nice clean source tree. Now we can take and make it by just going make GRLIB.MAK. Target does not exist, so it takes and runs the compiler to build it. So now we've automated building our library here. Take in, there we go. Our header's in the right place, our lib's in the right place, and now at the 1 minute and 41 second, 141 mark here, we can write our heat map application. Alrighty. Now, we'll start by making a directory for heat map. I'm in. Okay, great. So let me go pull up my notes for the heat map. And this consists of a couple of files that we will need. I'll pull the data file over. I've already prepared it and it's on floppy. I just need to take and copy it over when we're ready. But now we can actually start writing the code that does the heat map data. Actually, let's go ahead and copy that file. Let's go ahead and copy the data over. We'll build it iteratively, piece by piece. Let's see. Existing image. Excuse me for a moment. There it is. There's our example file, but there's our h.dat file. We're going to take and pull that into here because we're going to use it. Okay? There's our h.dat. Now, heatmap.c. Okay. Same song and dance as before. And yes, this is my email address. The license for details. Okay, fine, whatever. We need, first and foremost, since we need file I/O functions, we need standard I/O and we need standard lib. Because we're going to be using the standard C functions to do our file I/O. Might as well bring that all here ready to go. Secondly, what type of data that are we going to be dealing with? Well, it's binary data in a very specific structure. We call it a heat map structure. And the heat map data is serialized as a grid of 128 by 128 points, which we just take and collapse out into 16,384 possible points. That can fit okay on the stack, no problem. Name, Then we have an 80 column space for the name of the heat map data. We have a timestamp indicating when this sensor data was captured, and we have a description indicating what was happening at this particular point in time with that heat map data. Oh, let me change 17 real quick. And it's going to be referenced as a variable called HM. You can see it right there. There's our struct heat map HM, ready to go. Okay, great. Now we'll take an 18i. Here we go. First things first, we need a main function for sure. We're not going to be using any argument processing here, but if we did, it would be argc and argv, just like any other standard C program here. We're just going to do this very quickly and read from an h.dat that's sitting in the same directory. Very simple. Main, nothing special here. So the first thing we're going to add is we're going to take and read data. If we can't read the data, then we take and like that, and we return an error code of 1 from our main loop. That's the end of that. So now we've read the data, we can take and display the data. And then, oops, sorry. Why did I do that? That was a mistake. Display the data, 28. All right, fine, sorry, 27. F3, display data. 28 becomes, then we take and display, then we take and do the legend. Then we take and wait for a character. And yes, GR mode, old mode, and return 0. A couple things I need to add. No problem. Let's have a look. First thing we need to do, we'll insert at 21. Int old mode equals gr mode get mode. We defined get mode as part of GRLIB. Oh yeah, we also need to do that, don't we? So I need to come all the way up to 10i real quick because I can see it right there. Include GRLIB.H. Here we go. GRLIB.H, our data structure, get mode, and then we finally take and 23i, we'll take an insert right there. GR mode, and we want it to go to OXOE. I forgot what I defined it as, so we'll just put it as that. Okay, fine, whatever. 0x0e. Yes. Yeah, I think it was that. We'll see. All right, so GR mode, and list. Okay, great. So read data, display data, legend, and get care. So we'll go ahead and stub this out. Read data. Display data. Legend. Get those in and ready to go. Those are now in place. Let's see how we're doing so far. Exit. PC Heatmap. Oop. Get mode undefined. Okay, so what did I call it then? Mode get. EGA mode, okay. Mode E, okay. Wow. Remember, I can't even remember what constants I set from one moment to the next. I'm special. Not a problem. So I'll search for get mode. Modify F3, mode get. I use the S function there to search for the next stream of get mode, point the cursor to it, and then I can take and do it. If you learn your command structures for these line-based editors, you can get edits done very quickly. The next one needs to be 36. So fine, we'll take and edit you. Mode EGA 640, 216. Like that. So that should fix those two issues. Let's see how that goes. Oop, syntax error, EOF, end of file. Really? Hold on a second, let's have a look. Oh, need a closing brace, don't we? So let's do that. 50i for the end of main. My bad. So there we go. Heat map is built, and it's probably not going to do much of anything. It's going to change the graphics mode, but we're not going to see anything on screen, but we'll be able to hit the key and move forward. Heat map. Sorry. Oh yeah, I need to see link it. And of course, link against GRLIB. Bam. Okay, good. Yep. Can't read h.dat. Okay. Fine. Because we're not passing anything in. Well, that's okay. That's okay. Fine. 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 We'll make a little adjustment here too, so that when we die, we instead, 39i, we insert right here, sorry, 40i, at line 40, we go ahead and set the mode back. Get care. PR mode. And then return 1. Just to be a bit more hospitable. Control Z. All right, let's have a look at that real quick. 33L. Okay. Yeah, looks good to me. Fine, fine, fine. Now read data is, we're not passing back a return value yet, but it did do this for us. That's cool. We'll edit, save that. Fine. We know it works, so now we can actually start implementing the other bits and pieces. Let's go ahead, point ourselves to the top of the file, one list, one, and then search for read data. Boom. Okay, good. So now there's that. And line 22, now we implement read data inside the braces here. This is very simple. Since this is a binary file with a well-defined struct, all we have to do, fopen the file. If it's okay, we fread the whole thing into the data structure, and then we close it. File fp, fopen, h.dat. Yes, fopen did exist back here too. h.dat will read it as a binary. And this is a peculiarity of Microsoft's implementation of C that everybody else in the IBM PC actually took and appropriated, which was the distinction between reading binary files and text files. Okay, so we get the FP, and if for some reason FP doesn't open, let's say we can't find the file, whatever, if not FP, then we say, if not FP, then we return 1 because we're already doing the test here. So there we go. Bam, bam, bam. Groovy. Otherwise, we f-read this sucker, and we read it into the address where HM sits. Size of struct heatmap. And only one of those. We're only reading one heat map of that size from our file pointer that we just opened. That's it. We can check for a length, but you know, we're not going to. We're just going to read it in. Fine. And then we'll take an F close. And that's our file reading function right there. Bam. Now at this point, we'll have the file read in, it will be sitting in the variable HM, and then we can start displaying things from it. So fine, let's start filling in some of the bits and pieces for display data. This is simple enough. All we really need to do, we'll start by basically just saying, okay, grtext. Remember that we have a name. We have a timestamp. Again. And so that we don't scroll off the screen accidentally. Oh, never mind, doesn't matter. So, okay. So there we have our three little bits and pieces of our graphics text right here. What did we actually do here? So let's take a look. We look at line 34 list, we'll see display data, grtext, hm name, hmts, hf description, right there. Ready to go. Okay, let's see if this works. Well, it compiled okay. Let's see if it links okay. It should. Can't read h.dat. Oh, what happened? Do we have h.dat? We do have h.dat. Okay, let's do a little debugging. Oh, I need to return 1 if it's okay. Excuse me. That's what I did wrong. .4L. Okay, let's come all the way down here to 32i. And return 1, also known as true. CC heatmap. Okay, very good. Let's try that again. But you'll notice it reset the graphics mode back correctly this time. GRLIB. There we go. There's our description data from our heatmap data. So we know that we're reading our data structure at least partially correctly, if not completely correctly. We'll see in a moment when we try to take and plot the actual heat map data. First, though, we're going to go ahead and build a little legend. Building the legend is easy enough. We just need to take and display a series of boxes, you know, little color chips of sorts, and put text right next to them. That's easy. So let's find where legend is. Okay. And then at this point, we can then 44i and come right here, in between here, and start implementing. Well, it's going to be a loop because we're going to be outputting this in a loop. So we need an index for our loop. And we need a little area for our legend text. And the quickest way to do that is basically just to set this up here and then define it. So we could define this statically as a global thing too, which is what we would have to do here. But I'm trying to get this done. So 20 degrees C, 1, which is 25 degrees C, 2, 30 degrees C. And I'm using asterisk here because I can't type the actual symbol for degree here, but potential improvement for the program. Greater than 55 degrees C. Now, as a reference here to show how this actually is set aside, if I go and look at the file, let's go take a look at it. Let's use hexedit to look at it real quick. It is essentially a series. The heat map data is at the start of the file, and it's just a bitmap where each pixel is a given color from 0 to 7. So 8 possible colors in every case. So all we really have to do is take that data array, walk through it, and plot each color pixel the color that we need. That's it. And we can take and go ahead and use that information to plot the legend here too. So now that we've got our legend text implemented, I is less than 8, I plus plus. We do a little bit of gymnastics. We make little bars, and for each one, we're going to start, since the heat map takes up pixels 0 to 128, I figure 256 is a good horizontal position to start. And each block is 8 pixels wide, plus 16 plus 8 I, just like that. So 256 I, oh sorry, let me do that again. So 256 I times 8 plus 16, and then the X position stops at 264 I times 8 plus 16 plus 8 I, so that we get sort of a little width there. Just quick and dirty. I know it is. And then at that position, relative text position, this is text position, not pixel position, we put X and Y, we put the appropriate text for that index. And that's all we have to do for the legend. Go ahead and compile, we should be okay. Oops. Are we actually calling it? That's a question I have. Let's see if I'm actually doing this correctly. Oh, wait a minute. Let me fix that real quick. Of course, okay. Let's look down, okay. Yeah, GR bar. Okay. 34 I plus 2 T of I. There we go. Should be okay. I wonder. It's like we're not doing it at all. Am I calling legend? I am calling legend. Huh. Okay. Well, let me do a little look here, and we'll make sure what's going on here. Give me a moment. Okay, so I have a bug somewhere in GR_bar. Let me see if I can find it. We'll fix it and rebuild the library and get this going. Oops. Okay, so we'll stop here. Okay, fine. Let's go ahead and go to GRLIB. And let's debug GR_bar. Okay, fine. We're going to do a quick little look here to make sure that this is okay. X1, Y1, X2, Y2, C. X1, Y1, X2, Y2, C. Okay, color. Very good. Show. Double sure. Let's see. Make sure that that's okay. D is 1. X is Y2, Y1. Or D and H. Otherwise, -1, Y1, Y2. And let's look at 24L. We do. So that's GR line X1, Y1, X2, Y1, C, Y1 plus while, That looks perfectly fine to me. Why did you? Very interesting. Okay, let's check the, that's abort. That's nothing issued. GRLIB.H. Let's have a look at the bar. Short care. Yeah, GR_bar. Short care. Very good. No, what could it be? Let's go back into Heatmap. A little bit of a debug here. So let me go back in, search legend. Okay. I'll put that little bit back in here. All right, so GR_bar. I times 8 plus 16, 264. Y times 8 plus 16 plus 8, comma I. Yeah, and see, I is the current color that we're going to use, and that's perfectly fine. PC Heatmap. We'll try it again. C-Link. Heatmap. GRLIB. And try it again. Oh wow. I have to say that's pretty abstract, but hey, we have legends. Oh, it's like wow. That's freaky looking. Okay. That's interesting to say the least. But hey, we have legends. It's a nice look. Yeah, okay. Well, I'll take it. We'll see if we can spend a little bit more time on it and try to fix this real quick. If not, then we'll just take and go on without it. But yeah, there's our legend. Oh boy. Okay. So there is something goofy going on with GR_bar. What is it though? That's like freaky. Is it because is it literally because now we have prototypes and it's swizzling and I was literally banking on something not happening here? Let's see. I'm going to try something here and just see if this will give us something that we, I'm going to try getting rid of the function, the 15D, 15 to 16D. All right, so there we go. Save that. I'm going to see if this fixes it. If it does, I'm going to laugh because I'm relying on something stupid here. Oh shit. GRLIB. Let's see what happens. Okay, no, so I'm obviously doing something very wrong in the in the legend here. I could just waste an unbelievable amount of time here, but I guess I'll just move on. Oops. That's pretty funny though. So GR bar needs a little bit of debugging. As we fix it, we'll be able to take and come forward. But for now, let's just move forward and get the last bit in, and let's plot the actual data itself. And that's pretty easy. Famous last words, but it's pretty easy. So now at this point, we have this gigantic array of data. Heatmap C, okay. And it's sitting here in data, 16,384 bytes of it, and we just need to take and serialize it out. Displaying that data is pretty easy. So starting at line 37, we will then take and start defining some variables here. We'll have an offset as well as some X and Y coordinates. Sorry. Come back to where I was. We need X and Y. And we need offsets for X and Y. Because we're basically reconstituting this back into a 128 by 128 matrix. And to do that, we use a set of for loops. Y0, y is less than 128, y plus plus. And that immediately, it's a nested for loop. So immediately after that, for x equals 0, x is less than 128, x plus plus. And we just grp set xo, yo, hm data, and whatever the data happens to be at that offset. This is why we have the separate offset variables here. XO plus plus. Okay. That's the inner loop with the X data. Then when we reach the end of that line, we reset the X offset back to 0. We set the Y and we increase the Y offset, while O itself keeps marching forward. And that's everything that we need to do in order to plot our heat map data. That's it. We take a look at what we've done here. Display data. And look at it from this point on. Oops, sorry. Too far in. Oh, wait a minute. There we go. 35L. Excuse me. There's our completed display section right there. Setting up the variables, looping through, plotting each bit of the data, and then displaying the metadata down there at the bottom. And that's it. So we go ahead, we save that out. Then we take and build CC Heatmap. And then CLEAN Heatmap. GRLIB with our graphics library that we had to hand roll. And there's our data right there, plotted out nice and neatly. Our legend is a little weird, but it might take a bit too long to debug why that's happening, but I'll call it artistic choice. Wow. But here you go. You can see our heat map data got plotted out. Our metadata is on screen, and everything is as it should be. Compares quite nicely with the Amiga version, I think. We'll do the Amiga version once more for comparison. Coming back into my workstation. I forgot that I closed it completely. And you'll see one of the things that you'll notice as we compare here, the Amiga is able to take and mix and match display resolutions, display palettes, so that it can take and segment up the screen into areas with where the bits and pieces of information that are being displayed will be displayed in the display characteristics that make the most sense. You'll see here in just a moment. We'll take and open this up so we can compare. Because currently, right now, the PC is having to use a single resolution for everything. So we had to pick a very particular compromise on the total number of pixels on the display versus the total number of colors that we know we need to display for everything. Whereas with the case with the Amiga here, we were able to basically take and split everything out so that the low resolution screen that had more colors could be used to display the heat map, and the high resolution portion of the display could be used to display the metadata text for the heat map here. To take and further illustrate this point, we can go ahead and make a few modifications. We'll just change the graphics mode. With SGR mode, that's on line 81 here. And yeah, okay, mode, that's not this one, but well, here we go. And we'll change this to the next mode down, which is 320 by 200 by 16. And you can see it's drawing in 320 by 200 here, but you'll see very quickly that we run out of text space for the bottom part of the description here, so it accidentally scrolls off the screen. So we would need to take and potentially move this up a bit so that we could take and utilize the screen a bit more effectively. But these are part of the compromises that you need to deal with and effectively do. So. It's just an example, but you see right here that because we're using the BIOS functions, it's very easy to take and retarget this for other graphics modes. I mean, if I wanted to make a quick version of this for CGA, well, I can do that. I can use, let's say 85, sorry, not, sorry. S. OXOD, sorry. There we go. So that's line 82, so we'll change that. Let's change that to 4, which is 320 by 200 by 4, right? Edit, we'll take in CC Heatmap. And then we'll C-link Heatmap again. Oh God. Try it again. It's been a long day. But you can see right here, it retargeted for CGA. Although we will have to do some remapping of the colors, the quickest way would literally be just to average everything down so that it fits within 4-color display by shifting everything right. But, you know, there you go. I was able to take and switch graphics modes, and things were able to take and work relatively close enough. I will show a fundamental difference. Let's do one final change here so you can see. 83, sorry, 82, there we go. The GR mode, and we will set mode, hex mode 10, which is EGA, which is 640 by 350 by 16. Now this presents a different text mode with more lines on the screen and with a different size font here, so the text metrics won't match up exactly. But you can see it's working in 640 by 350, but you'll see that the text metrics are a little bit off. They have to be adjusted. Now the chips have to be 14 lines tall instead of 8. But, you know, there you go. I'm able to take and switch between different graphics modes. If I wanted to take and make a version that ran in PC Junior's 16-color graphics mode, all I would have to do is change the mode number and so on. So while the BIOS routines themselves are very slow, very inefficient, they are somewhat retargetable, as we can see right here. I hope this has been a good comparative analysis of writing an application for scientific or engineering purposes and seeing the differences between writing this on, say, an IBM PC AT versus writing this on the Amiga. The Amiga version's been covered in previous videos here, and this just adds to that whole discussion. Coming up, I will actually be showing how to do this using the Atari ST and its GEM operating system routines, VDI, AES, and the like. Now, it's rather interesting that I bring that up because, as it happens, if we look at WinWorld PC again, IBM actually licensed a copy of a graphical kernel system and sold it as an IBM labeled product. Give it a moment here, it's still spinning. So we have the graphical kernel system, and basically you can think of it quite literally as an implementation of an equivalent of, say, GSX, which was used as the bottom layers for GEM in the form of VDI. So GKS was a very prevalent graphical system that was retargetable and had a lot of drawing primitives that you could use for drawing geometric shapes, for filling them with all sorts of different patterns, for taking those drawings, etc., and outputting them to a variety of different devices. You see there were other additional development packages that were attached to it, like GFS, which allowed you to take those drawings in that drawing context and serialize them out to files and then bounce them back again. Those were called meta files. Plotting system, which added additional plotting functions on top of GKS, graphics terminal emulator for Tektronix emulation, that sort of thing. But all of these things were available for customers that needed them, that felt that they needed them. If they had written something on, say, PDP-11 or a VAX or a Sun running GKS, you could then take and side port it across to run on the PC. But it's worth noting that this particular piece of software, this is a $500, the GKS itself was a $500 package all by itself. So if you are trying to bootstrap something and you're trying to prove that you can write a piece of software to visualize something that's coming in from somewhere else, like we've been doing here, you may not have the latitude of your budget to be able to go out and immediately say, okay, I'm going to take and spend $3,000 on development software to take and prove my point. And you may have to just take and bootstrap it yourself. And this is where the Amiga honestly came to shine, because its built-in graphics functions allowed you to take and put something together that was very compelling very quickly. And with Windows, mouse, interaction, pointers, lots of colors, mixtures of resolutions, that sort of thing. Whereas on other systems, you would have to take, we're going to have to take and adjust these things for different target systems. For the Atari ST, the constraints of GEM, for the IBM PC here, we had to roll our own graphics toolkit. But these are the things that you had to do in order to get things done. So with that, I'm going to end this here at roughly the 2-hour 30 mark. I thank you guys very much for those of you who have stuck around, who are enjoying this content. If you haven't, please like and subscribe. I'm not getting anything from this content. I'm just hoping that people find this ultimately useful and insightful as to a part of computing that has been very underrepresented. That is, people had workstations or did computing, scientific and engineering tasks. Well, what sort of tasks were those? So anyway, I hope you guys enjoyed this. So I hope you guys are all having a wonderful December. And until next time, guys, have fun.